Ion exchange chromatography, or IEC, is column chromatography referring to the separation of ionic substances using an insoluble ion exchanger as a stationary phase and separate samples based on their differences in retention time. These variances are due to their differences in net charge and degree of ionization during their time in the column, pKa. This technique can be applied to a wide range of acidic or basic samples whose charge varies with pH. It works by utilizing the primary exchange of ions between the mobile ions of the sample and the fixed ions that are covalently attached to the molecular lattice of the ion exchanger, which happens when the sample passes over or through the ion exchanger stationary phase or zeolite. The ion exchange takes place based on the fact that for every ion that enters the solid, one of the chemical equivalences must leave to keep the system electronically neutral. Whilst this is taking place, some secondary reactions can take place. For example, a proton and a weak anion will bond and create an uncharged species, but generally all exchanges are reversible. The position of equilibriums can vary widely, and this variation is what makes the type of chromatography possible. The stationary phase for IEC is always an ion exchanger of some sort. Naturally occurring zeolites were the most popular when this technique was first developed, but strictures like molecular sieves are becoming more popular. In general, an ion exchanger needs ions of its own that can move freely in and out of the structure, and despite the fact that most exchanges occur on the surface, an open structure with channels and cavities for the mobile ions is best. As well as free ions, the exchanger should also have electronically charged groups anchored to the structure that can act like fixed ions. The exchanger used to pack the column is used based on an organic structure like polystyrene with substituted groups attached. Usually the polymers have to have at least 4 CH2 groups and a benzene ring. The functional groups added to the hydrocarbons are usually groups like SO3H and CH2NR3Cl that are ionized first to give ions, for example SO3- and NH4+, and the mobile ions H+ and Cl-. Exchangers that are weak acids or bases have special applications in biochemical analysis because their capacity to exchange with other ions, the H+ and OH-, can be adjusted by regulating the pH, which can help to deduce the type of compounds in the sample. The mobile phase is usually water or a buffer mix with or without the salt. The retention of compounds are also due to ion exchange, but this time between a mobile phase ion, M+ or M-, and an ion of the compound with a similar positive or negative charge. The equations for this type of interaction are shown on the learning pack and are very similar to the equation for the ion exchange within the stationary phase. As you can imagine, a lot of samples have ionic properties, so could be analysed using this technique, but a good example of IEC's use in industry is for water analysis and amino acid identification. Water analysis usually consists of the analysis of ions present, for example Cl-, NO3-, and SO4-, whilst amino acids analysis focuses on cation exchange and is detected after it has been eluted and treated with ninhydrogen. Amino acids are special cases because you get an amphoteric ions that can lose or gain a proton to get an anion or cation depending on the pH. This property means that a pH gradient can be used to separate the amino acids. Usually the pH gradient starts at around 3, forming cations, and increases either continuously or in steps. The dibasic amino acids with their 2 carboxylic groups are eluted first, followed by the neutral amino acids and then the dinitrogen amino acids that tend to be held so strongly that they often require further analysis in another column using a second sample and a strong elutant. The order of elution for neutral amino acids shows the effect of attraction of hydrophobic interaction, hydrogen bonding, and attraction of aromatic rings to hydrocarbon matrix of the ion exchanger. To get a better separation, the buffer composition can be altered, as can the temperature of the column and the pH.